So in example 2, instead of doing a table of values to find this, what we're going to use is the strategy of factoring. And this one off to the side is actually a really easy one to factor. Why is this one an easy one to factor? They all have x's. So we have a common factor of x, and so we can take that out right away. And that's going to make your life a lot easier than trying to do the synthetic division and find possible factors that work. So once you've got that one factor out, then the rest factors really easily as well. And if we want to find our x-intercepts when it's equal to 0, we get x equals 0, x equals -3, x equals 2. This is an x cubed graph, which means it acts like a line with a positive slope. So we would have 1, 2, 3, -3. We would have 0, and we would have 2. We would have no y, well, we have a y-intercept, but it's already at our x-intercept, so you don't have to actually figure it out further. And since it acts like a positive x cubed, like a line, this would be our final graph. Now we are going to look at the one in the example as well. So in the one in the example, this one is harder to factor. It's an x to the 4 graph. So you would have to try different values of factors of the -6. So you could try plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. Attempting those different ones, again, mental math-wise, it's going to be easier to plug in smaller ones. If we plug in 1, we happen to get 0, which tells us that x minus 1 is a factor. So we could set up our synthetic division to -1, -14, 19, -6. Again, I do a quick check to make sure that none of my powers are missing. Yes? Okay. And then the number outside, I would put a 1 here. So again, one of the ways I can do a quick check that none of them are missing is my highest power is x to the 4. I should have 5 numbers if none of them are missing. Or you can just check. I've got an x to the 4, I've got an x cubed, I've got an x squared, I've got an x, I've got a constant. Good. So now we can bring down the first number, multiply and add. And sure enough, we get a remainder of 0. So we can write our first division statement. We now know that f of x is equal to x minus 1 multiplied by 2x squared plus x minus 13x plus 6. Now, if I call this function here g of x.
I think you messed up.
Yeah, that, oh, look at that. I did. This is nice. Save. Perfect. So we'll call that new one g of x. And now because it's an x cubed, you're going to have to do the same thing again. You're going to have to test different values in g of x. Now, if we try those different values, we find out that if you plug in 2, it happens to be 0. Now, chances are you would try 1 first. 1 doesn't work. Then you try -1. -1 doesn't work. So it might take a little bit of time before you find out that g of 2 is equal to 0. And then once you have that g of 2 is equal to 0, that means that x minus 2 is a factor. And so if we put the values of g of x, 2, 1, -13, 6, and put a 2 outside and do our synthetic division, we can now write our division statement for f of x. We knew from the first one that x minus 1 was a factor. And now we know that x minus 2 is a factor, and we're left with 2x squared plus 5x minus 3. And finally, we have a quadratic function, and so we can factor this again. And you can see in these questions where we're factoring within a bigger thing why all year I've sort of been leading you to try to be able to do this in one step so that it just flows in your work and you're not having to do a bunch of work off to the side. Again, this isn't a hard one to factor because it has to be 2x and x to start. Our last numbers have to multiply to get 3, and I need to get a 5. So if I put a 3 here and a 1 there, my outside will be 6, my inside will be 1. And I need this one to be positive and this one to be negative to make a positive 5. This is a tricky one to factor because if you put the 3, I'll just write it in green above. If I put the 3 here and the 1 there, my outside's 2 and my inside's 3, and that makes 5, but it only makes 5 if you're adding. And because our last number is a negative, that's telling us that we have to have it subtracting. If our last number was a positive, then we're looking for numbers that are adding. So as you do more and more factoring, you'll start to see some of those patterns come through. So with this one, with the last number being negative, with our outside and our inside numbers, we needed them to subtract to give us 5. So all of that just to factor. The question didn't say factor, it said graph. So now that we have it completely factored, we know that we have an x-intercept at 1, an x-intercept at 2, an x-intercept at a half, and an x-intercept at negative 3. If we plugged in 0 for x into the original function, we could find out that our y-intercept is at negative 6. This was an x to the 4 graph that's positive, so it's going to act like a positive parabola. And now we just need to go through all of our points to sketch our graph. It seems like I was a little bit slopey here, eh? So chances are in real life this would probably come down, go down further and then come up like that. That looks like a more smooth kind of graph. So if your graph looks awkward, it probably is. But as far as a sketch goes, that would be acceptable. You need to show a nice attempt at a smooth curve. If you get overzealous, you will lose marks on your final exam if your graph goes, whoa, I went too far, there we go. That's okay, because now this is no longer a function. It doesn't pass the vertical line test. So you will lose marks for the shape of your graph on quizzes, tests, and the final exam if your graph goes a little bit too crazy. So it needs to be a smooth curve through those points. We don't want it to end up not being a function, so that's bad. But either the black or the green would be fine. And if you want more ones that don't have multiplicity, that you have to factor first, questions 7 and 13 are good examples.